Okay, for today's video, we're going to introduce an equation that we can use when we know the speed of sound, depending on the material or the medium in which the sound is traveling. Um, in order to have this conversation, we're going to delve into today wavelength, and then we'll continue tomorrow with looking at examples of how we can use this equation in what we're doing, as well as tomorrow in class. Now, our objective for this week, as just a review, is that I would like students to be able to solve a variety of problems concerning the speed, frequency, and wavelength of sound waves. And then the second objective is we will compare the three main mediums through which sound can travel. So just to focus a minute on the objectives in these command terms, we have solve and compare. So we will solve a variety of problems. What does that mean? So basically, solve is an indication that we need to obtain an answer using numerical methods. So what sort of math are we basically using in order to solve for a problem, to get a final answer? In the second objective, we're talking about comparing the three main medians through which sound can travel. So comparison would look like this, giving some examples and explanations as to the similarities and differences between two or more items. And our two or more items are going to be solids, liquids, and gases. And the best way to think of those is air, water, and something like steel, for instance. Okay, so let's begin our conversation with a talk about wavelength. So first of all, let's define what wavelength is. Wavelength, which is identified using the Greek letter lambda, is basically the distance from the beginning to the end of a wave. So as an example, let's go ahead and take a look at the wave below. And notice that on the wave we have a bunch of different points that have been identified. We have A, and then what's called A1, C, C1, D, D1, and B1. And the idea behind those marks being there is that basically we are just going to look at what represents a wavelength. Now usually a wavelength is measured from the crest of one wave to the crest of another. So if we look at A and A1, mark it with a line, that would be considered a wavelength. But we could also look at a wavelength as being the distance between the trough of one and the trough of another, or that valley. So between B and B1 would be considered a wavelength as well. And we don't have to stop there. We could basically just look at the distance between one corresponding part of a wave and the same corresponding part of another wave. So if we look at C to C1, that would be considered a wavelength, and D to D1 would be considered a wavelength as well. So what really matters is that no matter where you're measuring the wave, you're measuring that distance from one spot on a wave to the same spot on a different wave. And notice it doesn't matter if we look at A, C, D, or B. If we look at the lines that we've formed for each one of those, no matter what, they're going to line up to the same distance. So the distance isn't going to change depending on where you measure. It's just common practice to measure from the top of one to the top of another, or the bottom of one to the bottom of the other, and that's just because it's easier to see it that way. So these are basically what we would use to measure the wavelength of a wave, and in this case we're talking about sound waves. Okay, so let's have a little discussion then about what affects wavelength. And we've talked about two things somewhat in depth so far, which is amplitude and frequency. So what impacts wavelength? Is it amplitude that affects a wave and its length, or is it frequency? And the best way to take a look at this is I'm going to draw a wave over the one that's already been created, and I'm going to get rid of the one behind it. And what we'll do is draw a line between the top of one crest to the top of the other, and that will be a representation of our wavelength. And what I'll do is I'll increase the amplitude. So notice if I increase the amplitude, that means that my wave is going to get taller and my troughs are going to get a little bit deeper. So I'll go ahead and increase the amplitude. Now notice when I increase the amplitude on this wave, the wavelength didn't change. However, if I change the frequency, in other words, if I tighten up those waves a little bit horizontally, then that has an impact on the wavelength. So what we can see here is that amplitude does not have an impact on wavelength, but in fact it is frequency. So what we could say is that a higher frequency, which leads to a higher pitch, so a higher pitch, a higher note, meaning more waves packed into an area, leads to a higher frequency. A higher frequency, which is again a higher note, means that we're going to have smaller or shorter wavelengths. On the flip side, lower pitch means lower frequency, which means our waves are going to be much more spread out, and that means that our wavelengths are going to be much bigger then. So as an example again, we'll go ahead and tighten up those waves a little bit more, and notice that we made a shorter wavelength, but in doing so we're going to have a higher frequency, which is going to give us a higher pitch or a higher note. So higher frequency, higher pitch, and that is due to a shorter wavelength. On the flip side, if we expand this wave horizontally, then notice the change that occurs. That shows us that we have now a much bigger wavelength than we had before, and this is going to lead to less waves, which is a lower pitch and a lower frequency, and that means bigger wavelengths. So basically the idea behind this is if you want high notes, which is a higher pitch, then you're going to have shorter wavelengths. If you want low notes, which is a low pitch, you're going to have much larger wavelengths then. Okay, so let's talk about the equation then that we're going to be using for probably the rest of the class period this semester in this study of sound. And to have this discussion on the equation, let's first talk about the components that we have in our first learning objective, which is speed of sound, and that's connected to this idea of wavelength, and that in turn is connected to something that we call frequency. So how many waves or vibrations do we have per second that are traveling through a specific distance? So speed of sound is typically labeled as v for velocity, so we can identify as a velocity, and speed and velocity are somewhat interchangeable. Velocity should be a vector which includes a direction. Now since speed is usually, or the speed of sound is usually not including a direction, it's kind of confusing to use v, but that's just kind of the typical thing that we see. So what's interesting about our equation for the link between these three concepts, speed of sound, wavelength of an object, and frequency, is that they basically involve a velocity or a speed, a distance, which is the wavelength, and frequency, which is kind of a representation of time. How many vibrations per second are occurring. So what we'll do is we'll take a look at an equation you guys are pretty familiar with, which is velocity equals distance divided by time. And what we can see is that if we split up distance and time into two fractions, which would actually mean that we're multiplying them, and this is something you guys have probably seen or done in algebra before, then what we're left with is 1 over time multiplied with distance over 1. And that will give us our equation, velocity equals distance over time. So we'll notice that everything above, all the three components that we've talked about, speed of sound, wavelength, and frequency, those match up perfectly to our velocity equals distance divided by time equation. So notice if we look at distance over 1, that's just basically wavelength. So wavelength is measured in meters as a distance, And so those two can correspond together. And then frequency is basically how many vibrations per second. So how many, how much, what's happening, I guess, every second that's going by, whether it's vibrations or the movement of some object. So in this case, we're talking about vibrations, but frequency matches up beautifully with 1 over time because frequency literally means per second. So how many vibrations per second, how many rotations per second, how many breaths per second, how frequently does that happen? And per second can literally be written as 1 over s, so 1 over time or 1 over seconds. And then last but not least, we have the speed of sound, which corresponds beautifully with velocity. So this literally is our equation. The speed of sound equals frequency, which is just some sort of indication of time, multiplied with distance, which is identified for us as wavelength. And so our equation is velocity equals frequency multiplied with wavelength. Now, what are we going to do with this equation? Well, this equation is especially good for finding things like distances between objects. So given the speed of the specific medium we're talking about, so if I'm floating in the ocean and I hear a sound through the ocean, then I can gauge potentially the distance between myself and the object that made the noise if I know the frequency and the wavelength of that frequency and so on. And so something we should notice is that a frequency has a pretty specific wavelength as well. All right, so we have tons of different frequencies, and based on the fact that waves get compressed horizontally or spread out horizontally, that changes not only the pitch and frequency, but that changes the wavelength as well. So every frequency or note has a specific wavelength that is associated with it. So distance between objects is a great one, and this has some application in some of the things that we've used in the past as humans, which include cameras that we can put on auto, which allows it to gauge how much should I zoom in or zoom out on an object. So how do we get that camera to identify that we're so close to an object and the object doesn't get fuzzy in our picture? And this again has a link to our velocity equals distance over time equation. So we'll be using both equations somewhat together, our sound velocity equation and then our normal velocity equals distance over time equation. And then we'll get into things like echoes as well, and how does that translate to distances and things of that nature. Cool. So tomorrow, don't forget to dress for the weather. We're going to be planning on going outside for a short amount of time, and then we'll be spending some time looking at using this equation in some applied problems as well.